So the rate laws that we learned last day, where we had 0th order, which was rate is equal to K, because it was concentration of A to the 0, which is just equal to K. We had first order, in which rate was equal to K times concentration of A to the 1, which is just A. And we had second order, where we had rate is, ooh, that's a nice E. We had rate is equal to K times concentration of A squared. Okay? So we have 3 possible graphs. We have concentration of A versus T. So, I'm getting ahead of myself. I got really distracted at lunch because I was marking, so my brain is like doing other things other than being involved with teaching you right now. So I'm going to switch gears. Clunk. All right. When a reaction proceeds too quickly and you cannot get a consistent initial rate, why would it be important to find an initial rate for determining which rate law you have? 0th, first, second. Yeah. Because that's the method, right? That was our first method. So methods to find the rate law. Number 1, we had the method of initial rates. That's what we did last day. And today we are going to be doing from graphs. And this gives us the integrated rate law. Now, if you've done any calculus, you might know what integration is. You don't need to know how to do integration to be able to do this. Okay, you just need to be able to see if a graph is a straight line or not. Okay, and push a few buttons on your calculator. The rate laws that we looked at before, normally we would just call those rate laws, but sometimes they will call them differential rate laws because they're the differentiated ones and these are the integrated ones. But again, those are just titles at this point in your lives because they don't expect you to have done calculus necessarily. Okay, so we don't need to worry about that. But the gist of it is, if your initial rate goes too fast and you can't get a consistent reading because, you know, the concentration of the reactant is dropping too fast, so your initial concentration is not steady, yeah? Then what we have to do is we have to collect some data over time, okay? So we collect concentration data as time goes on, and that would be using one of the methods that, you know, we talked about for the last quiz. You know, you could look at spectrophotometry or gas collection or whatever. And you're going to graph. You're going to start by graphing. Concentration of A versus time. And if you get a linear relationship, do you guys know what it means to be linear? If it's linear, that means it is a straight line. So if you graph concentration versus time and you get a straight line, then you know it is 0th order. If you don't get a straight line, then you can say it is not 0th order, and now I need to try some other things. And there are 2 other things that you will try. You will try taking the ln of the concentration of A. Do you guys know what ln stands for? It is the natural log, and often we pronounce it ln, okay? Okay, so we pronounce it ln, and it is the natural log. And it stands for log base E. And E is some weird irrational number that I've never really understood, okay? Because I'm not a mathematician, I'm a biochemist, okay? So, you don't need to know what it does or how it works. You just need to know that on your calculator, there is a button that says ln. And if you have not yet seen that button on your calculator, please pull your calculator out now and find that button so that you know where it is. You will also need to use it later today. So pull out your calculator. Find your natural log button. And we've got natural log of concentration of A, and if we graph that versus time, and if we get a linear relation for that one, so if we take natural log of A, and if that is linear, in other words, if it's a straight line, then we have a first order reaction. If neither of those gives you a straight line, by process of elimination, you should be able to tell that if it's not 0th order, if it's not first order, it's going to be second order. But if you're asked to justify your answer, you would also want to graph the third one. And so the second way of straightening a graph is to take the reciprocal of A, in other words, 1 over concentration of A. And if at that point we get a straight line, remember linear means a straight line. Where did my green pen go? We get a second order reaction. So mainly this is about recognizing which graph you're looking at by looking at the axes and saying which one's a straight line and being like, oh, I know that order, okay? So you can choose the correct rate law. So for example, for 0th order, when we graph concentration of A versus time, we get a straight line. Does it make sense that the concentration of A is decreasing over time? Yeah, because A is a reactant, so its concentration should be decreasing. Does it make sense that it is 0th order? And what 0th order means is that the rate does not depend on the concentration of A. Because remember, concentration of A in the rate law, A would be raised to what power? 0. So what does that become? 1. And so our rate law is just rate is equal to K. Is there a concentration of A in that equation anywhere? No, there's no A. Okay? And that's why this is a constant rate. Right? It's not decreasing fast and then slowing down over time. And what you'll notice is that we have a slope and the slope is delta y over delta x. What is y in this particular instance? Concentration. So we're going to have change in concentration over change in time. And because k is always a positive value, and this has a negative slope, the value of k is always positive. You can actually find k by finding the slope and then changing the sign to positive. Or you could say that k is equal to the absolute value of slope. Do you guys know how to show absolute value signs? Like that, right? And I think that one's actually a little bit nicer because when we get into first order, k is equal to negative slope. And when we get into second order, k is equal to regular slope, not negative. But rather than having to remember to make these two the opposite sign in order to make it positive, if you just remember that k is always positive, so you're finding the absolute value of k, then you don't have to worry about whether you're making the slope negative or leaving it alone, okay? So you could also say that for all of these, for all of them, k is equal to the absolute value of slope. What else can we read off these graphs here? We can read off the y-intercept. The y-intercept is the at time equals 0. Time equals 0 seconds. And so that's going to be our initial concentration. And I have made a boo-boo here. I need to fix this. It shouldn't be concentration of A with a little 0 at the bottom and the brackets. It should be concentration of A, and the naught should be on the outside. Okay? So our y-intercept is the initial concentration, which makes sense. If we go over here, we say, this is time equals 0. And so this right here, this point right here is concentration of A naught at time 0. If we have first order, we will get a curved graph if we just graph A versus T. We'll take a look at that in a moment. But this is our straight line graph, and we get this if we take the natural log of A and plot that versus time. So all you have to do is punch that little button on your calculator. Or if you don't like punching buttons on your calculator, if you know how to use Excel properly, you can just have all of your times. You can enter all your times in one column. You can enter all your concentrations in another column. And then you can make a little function that says equals ln of the cell beside it. And it'll just calculate the natural log for you. And then you can copy and paste it down and it'll do that same function for you all through. Do you guys know how to use Excel to do stuff like that? Some of you do? Who does not know how to use Excel to do things like that? Never heard of it. Okay, that if we have a little time this year, it'd be worthwhile seeing. I don't know. We'll figure out if we have time. If not, they'll put you through your paces in first year university, so you'll learn it quick enough anyway. Okay, so we have natural log of a versus t. What is this value here at the y-intercept? It's the natural log of the initial concentration. So that right there is ln of a naught. Of course, our regular rate equation is rate is equal to K times concentration of A, because of course there is a little 1 right there that we just don't bother writing. Okay, that's good. Second order, you'll still get a curve if you do the ln of A. So if you do 1 over A, and you'll notice in this case the slope is positive. We have a positive slope. For first order, we had a negative slope. And remember, what's slope equal to? K. It'll be, K will be the absolute value of the slope. Okay, excellent, excellent. Good, so now we have concentration of 1 over A versus time. What is the x-intercept here? Or sorry, not the x-intercept, the y-intercept. One over concentration of A naught. Okay, and that's it for that. Now let's take a look at all the graphs. Next page has all the graphs. So let's look at this first set of 3 graphs. We have a straight line for A versus time. We have ln A versus time. That gives us a curve. And we have 1 over A versus time, which gives us a curve. What order is this reaction? 0th order. So this is the correct one here. So that is 0th order. And for first order, you get a slight curve when you graph A versus time. But it will straighten up nicely when you take the natural log of all those numbers. And then it will give you a different curve if you take 1 over A. So this one is for first order. Finally, we have second order. So K is, so we have, this is our straight line over here. And so this is our second order. And you'll notice that this is a, instead of being a slight curve, this is a bold curve, shall we say. I don't know, a more significant curve, a bigger curve, okay? I'm going to call it a bigger curve. So you might kind of be able to tell from if you got a slight curve or a bigger curve, which one of those others to do, but that's always a matter of judgment. So usually you graph all 3. Okay. Right, take a look at the next page, and I would like you to determine the rate law of this reaction. if we want rate law, what's the first thing we need to write? Rate equals K. And is this first, second, or third order? This is first order, because this, our ln of H2O2 is our straight line, so it is first order. And so what should we have after K? Concentration of H2O2, because that is our reactant. Okay, and that is our rate law. That's a straightforward kind of question, yeah? Now, if you're going to have any problem remembering like which one is which, like is it ln that's first order, or is it 1 over that's first order? The nice thing is that on the data booklet, in the kinetics section, let me get rid of all this nonsense here. They give you these 3 reactions, or sorry, not reactions, formulas. And these 3 formulas, this is a different way of writing the rate law. Instead of writing rate equals K times A, these are the integrated versions. These are our integrated rate laws. Okay. So those are our integrated rate laws. And you'll notice, what have we got in the first one? We've got concentration of A. It's not natural log, it's just concentration of A in that first one. And that is our 0th order. They go in order. Our second one is ln of A. Yeah, it uses ln of A, and that's our first order. And our last one is 1 over A, and that is our second order. So if you're like, which one should it be? It tells you right there. Okay, whichever one gives you the straight line. If you don't happen to have that, like if you go to university and they're not so kind as to give that to you and you think you're going to forget it, I came up with a very macabre way of remembering it when I was in university. I thought, okay, we have regular, and then we have ln, and then we're underneath. Yes, we're below. So I thought, okay, you start out your life, you're alive, you're just here, you're normal. And then you die, and what do? They dig up the lawn, and then they bury you under the dirt. I don't know. It helps me remember it. Yeah, I got a lot of those looks in first period too. People are like, is she a serial killer? Is this why she has thoughts like that? No. Okay, I'm just, anything that will help me remember is good. All right. Let's go back here. There we go. And now we're going to move on to the next page. So we're actually going to skip this section. If you're interested in it, you can do it. You can figure out y equals mx plus b and actually calculate the slope and all that kind of thing. We're just going to skip that because all this helps you do is to find the integrated rate law, and they give you the integrated rate laws. So do you need to find it from the graph? No. So we are going to skip those pages where we find the integrated rate law from the graph. So we're going to skip page 17. We're going to skip page 18. And we are going to then just move on to page 19. Okay? Now, this just says you've got those. When we want to actually find the value of K, you can use any two data points on your graph to find the slope. Yes, and slope, of course, is delta y over delta x, so it's y2 minus y1 over x2 minus x1. So we are going to go back to example 1 on page 16. I think it's page 16. And find the value of k for the decomposition of H2O2. Okay, so let's go back to page 16. I think it's page 16. And I will say that although you can read any point off the line, these data points line up really nicely. This is some cooked data here, I think. That's okay. Right? How often do you get data that really looks like that? Not very. Okay? But what that means is because every single point is on that line, you could use any of the data points in the table for your y1, y2, x1, x2. Okay, so I would have a tendency to go up here and maybe use the first and last point. And I would put my natural logs up here. And actually do the calculation. I did that wrong. Did you guys get 1.664 times 10 to the negative 3? Excellent. Okay, so if you're like, how did that happen? Just a quick go through. K is always equal to the absolute value of slope. And in this case, Y is ln of H2O2. So the change in ln of H2O2 over the change in time. And up in the table, I took the natural log of 0.50, and that gave us our ln of H2O2 at 0 seconds. I took the natural log of 0.0250, and that gave us our ln of H2O2 at 1800 seconds. Now that we have those two values, those are our Y values, plug them in there. What is the unit when you take the natural log? I don't know how that works actually, but as far as I know, it just natural log gets rid of the unit. Bye. It goes away. If you understand it from calculus, go ahead, but I don't know what the unit is. We can also, though, and if it does go away with the natural log, what that gives us is just seconds. So this is seconds here, and this is then seconds to the negative 1, and our unit would be seconds to the negative 1. I don't feel comfortable with that in terms of finding the unit, because to me that just seems like magic. Ln makes the unit go away. That seems like magic to me. So I would be more comfortable finding the unit of K by using the regular rate law, which in this case is, because it's first order, it's rate is equal to K times the concentration of A. That's our regular rate law. We will solve for K. K is rate divided by the concentration of A. And then if we toss units in that, do you guys remember what the unit for rate is usually? Molar per second. Okay, unless you're given it in hours or something like that, in which case change it to hours. Or if you're given pressure, maybe it's going to be atmospheres per second. All right, but usually it's molar per second. And so what we would have then here is we would have molar per second over, and what's the unit for concentration? Molar. And so our molar cancels with our molar, and we are left with 1 over seconds, which is seconds to the negative 1. So you can either say magic, the ln makes the unit disappear, or you can be like, okay, I will just use my regular rate law and find the unit for K using regular rate law. Either way, you've now got a value and a unit for your rate constant. All right. So now we can go back to page 20, page 20. Top part of page 20 is just working through that example. Finding the units of K. This just this just summarizes what we just talked about. You can either say, okay, on my 0th order, I have concentration of A versus time. So my Y value is A, that's my Y. So Y over X, my X is time. So that's my Y, that's my X. Concentration is molar, time is second. So the unit for rate constant for 0th order is going to be molar per second. Or you can solve for rate law. You can say rate is equal to K, and rate is molar per second, so it's molar per second. Okay. First order. Well, our Y value is now ln of A, and the X is time. And remember, taking the natural log, magic poof, the unit disappears. Okay, so that just goes away. You're left with a 1 over seconds. Second order, Y is now 1 over A, which means the unit is 1 over molar. And then we have time on the bottom, that's our Y, that's our X, over seconds. So we have 1 over molar seconds. Or, like I said, you can use the regular rate law, which is called the differential rate law. That's our regular rate law. Which is just, we have to the 0, to the 1, to the 2, and then you solve for K. And then you plug in the units. And you cancel out whatever you can cancel out. And you will end up with molar per second, 1 over second, and molar to the -1, second to the -1. And those could be written any which kind of weird ways. I don't know. I've actually seen second order written as liter mole to the -1, second to the -1. And I'm like, oh my God, that makes my head hurt. But okay. You know, if you have molar to the -1, that's liters over moles, right? And if you got second to the -1, that's 1 over second. So you got liters, mole to the -1, second to the -1. You would be perfectly fine writing it like that. Nobody's going to get mad at you if you don't go to the trouble of changing it to this for second order. Okay? So just realize that if you see weird stuff like this, that's where it comes from. If you see anything like that, you can be like, ah, that's molar upside down. Yes? 1 over molar. But I don't think it's likely they're going to bother you with any of those units, okay? This is just a summary table that I thought was kind of nice, so I put it in here. If you need to memorize it and you don't like my sort of morbid, you know, first year regular and then they dig up the lawn and now you're under the lawn. So if you don't like that, you can remember that it should be clear to you now, CLR, it should be clear to you that the integrated rate laws are what they are. So C, concentration. L, ln of concentration. And R, reciprocal of concentration. If you like that. But it's on your table, so you don't need to worry about any of those things. So, analyzing graphs, we've already talked that you should be able to determine the order given different graphs. If you are given the order, and you can see that it's a straight line, and you're given the order, you should be able to label the y-axis with the correct one. Given the order of the reaction, you should be able to sketch a graph, like the straight line graph, which one it is, okay? Problem solving tips. I don't know that this is any helpful. This is all, we've already said this. K is always positive and the absolute value of the slope. The one with the straightest line is always the appropriate relationship. And you know what the shapes of the lines look like. zeroth order, first order, second order. So we have negative slope, positive slope. Yep. Okay. There's some exercises which we are not going to do right now. We'll have a little bit of time after your quiz tomorrow to work on the exercises for the rate law and the integrated rate law. Okay? All right, so we are now on page 26. We can use the integrated rate laws that are given to us in the data booklet, which is these forms. These are the ones here that are given on AP data sheet. And we can use them to figure out how long does it take to react. We can figure out what concentration remains after a given time. And we can figure out what is the initial concentration. Because you will be given everything you need except for one unknown from here. So A with the little t at the bottom, that is the concentration that remains after a given time. So let me grab again the blue pen. There we go. A at time t, that's the concentration that remains after a given amount of time. Initial concentration, we already know that's A naught. And time, of course, is just t. So basically, you are solving the integrated rate law for whichever one is the unknown. You'll be given the k value, all right? And then Bob's your uncle. A little bit more information that's just on here. If you have zeroth order, that means you're just going to have one reactant, A. And for whatever reason, it just does not affect the rate of the reaction. If you have first order, you're going to have A, going to products. If you have second order, you're either going to have 2A goes to products, and your rate law is going to be rate is equal to Ka squared, or you're going to have A plus B gives products, and it gets too complicated when the concentrations don't equal one another. Okay, so we're just going to kind of not worry about that too much, because mostly what you need to be able to do is to take these equations over on the right-hand side and solve for either the blue, the green, or the yellow. Yep. What the heck is this over here? These ones? These are y equals mx plus b read off of the graphs. So you could come up with that on your own, and then you can actually rearrange it to find the format that they give you in the data sheet. But like I said, I don't think you're ever going to need to do that, so let's not worry about it. Okay, moving right along. How long does it take? You will be given the initial concentration. You will be given the final concentration. You will be given the order of the reaction. And you will be given the rate constant K. And with those, the only unknown is then T. So let us try this question here. And we're just going to take a look at this because it's got a couple little tricks in it. Okay? The rate constant for The first order decomposition of cyclobutane, C4H8, at 500 degrees Celsius is 9.2 times 10 to the negative 3 seconds to the negative 1. So what is 9.2 times 10 to the negative 3 seconds to the negative 1? What does that number represent? That is the rate constant, okay? So the first thing they're doing is they're separating what that is by a whole sentence length, okay? But now we've got that. And that's why you guys are AP students, because you don't get messed up by stuff like that nearly as often, okay? We are also told that it is first order. That's useful information. And we are asked, how long will it take? How long will it take? That means T is our unknown. We don't know what time is. And here's the tricky bit. How long will it take for 80% of the C4H8 to decompose? Is, if the concentration of A at time 0 is 100%, what is the concentration of A at time t when 80% is decomposed? Yeah. Does that make sense? So that requires a little bit of interpretation on your part, right? You need to be able to look at that and not be like, oh, I have 80% left. No, because 80% was used, you have 20% left. The other thing that's a little bit weird is that they've not actually given you any concentrations. But that's okay, because what have they given you? They've given you percentages. So the ratio between the two will remain the same. And you can just do things like you can say, let's just make up some values where we have 100% concentration and a 20% concentration at time t. So we could say, for example, assume that the concentration of C4H8 at time 0, I wouldn't actually use this one because this is ridiculous. There's no such thing as 100 molar concentrations of things, but you could. Do you know what I mean? And you could be like, 20 molar. These are unrealistic concentrations. So I would tend not to use those actual numbers. What might be more realistic? You could do 1 molar and 0.2 molar. You could also do, if you wanted to, you could do 10 molar and 2 molar. Okay, those would be more realistic. Yeah? So generally with a question like this, it's good to just organize your information. If it's a written response question, you can get down that K is equal to 9.2 times 10 to the negative 3. 9.2 times 10 to the negative 3 seconds to the negative 1. And if you happen to remember that the rate constant's unit when it is first order is seconds to the negative 1, then bully for you. That's great. But if you don't, they also told you that the order was first order. And time is what we don't know. At that point, you take a look at your 3 rate laws, 3 integrated rate laws from the data table, from the data sheet. Which one will we pick? Will we pick A? Will we pick B? Or will we pick C? Which one do you guys like? We're going to pick B because this is first order. So we're going to use this one. And then you plug everything in and do the math. Why don't you guys just try plugging everything in and doing the math? Okay? just to make sure that you can plug the buttons on your calculator correctly, especially because this is a natural log one. And for some of you, this will be the first time you've used natural log button. There's another reason to make your 100% 1 molar, because the ln of 1 is 0, which makes your math really easy. Did you guys get 170 seconds? Yeah? Excellent. That means I did it right. That's exciting. Okay. And normally I'm in favor of like solve for t and then plug in, but when you have to like do things like take the lns first, sometimes I'm like, just throw them in and then solve for t. It's okay either way. So that's solve for t. What else have we got? We have how much remains after a given time. Well, that is how much remains after a given time. What quantity is that? What variable is that? Concentration of A at time t. So how much remains is the concentration of A at time t. So A little subscript t. So you need to know all the other things. You need to know concentration of A, initial concentration. You need to know the time, order of the reaction, and the rate constant. And then you substitute the information and solve for A at time t. So here is another question here. The reaction of butadiene. Do you guys know what the ending "ene" means? Ene means you have an alkene. Okay? And an alkene has double bonds. Can you guess from this name how many double bonds? 2, because we've got diene. So we have 2 double bonds. And then this is buta. How many carbons for bute? 4 carbons. Could you draw, you don't have to put the hydrogens on, could you draw a structure where you've got 4 carbons and 2 double bonds? I don't know how well this is going to go. We'll see. I would tend to do it that way. That's going to be more stable, right? With the hydrogens coming off. I mean, I suppose you could do like that. But that just seems less stable because this carbon right here has just a lot of stuff crammed around its center. I don't know. Don't worry, you'll never have to draw this until you get to organic chemistry. And then they'll probably tell you it's 1,3-butadiene. Carbon number 1, carbon number 3, that would be 1,3-butadiene. And this would be 1,2-butadiene. Or, yeah, something like that. Anyway, the naming system makes some kind of sense. But anyway, let's not get too worried about that. I'm just making up stuff because we have extra time compared with the other block. We didn't even make it this far. Okay? So what time is this class over at? 16? Oh my God, we got 10 minutes left. Gee whiz. Okay, we'll keep going. Distractions aside, how about you guys try this one on your own? Do you want to do this one on your own? Do you think you can? I think you can. Write down your given information. Choose which form of the rate law you'll plug it into. Okay? Mm.
Did you guys get 0.0179? No? Uh-oh. I apparently got it last time I did it too. I got 0.179. Did you get 1.179? Okay, so now I actually wanted to show you this because I did not space out this problem very well, so my organization is poor. If your organization on a question is poor, you should organize it so whoever's marking it does not have trouble following. So what I've done is I have labeled step 1, I've labeled step 2, and I've labeled step 3. Yes, that's going to help, right? And I might even put step 1 just to help. Step 2, step 3. Assume that whoever's marking it is an idiot and they don't know what they're doing and they can't follow your work, okay? Be kind to the idiot, okay? So we have our, I decided not to throw my numbers in right away. I decided to solve for 1 over a. I didn't want to do like the reciprocal of it. That sounded like too much work. So I took this and I moved it over here to the other side. Yep. And then I really did not have enough room here, so that's down here. Yeah. And then we had KT. And I sort of made a note for myself that liter over mole is molar to the -1.
And molar on the bottom is molar to the -1. So my unit, when I get this, is 1 over A at time t. So if I want to find A at time t, then I have to take I have to take the reciprocal of that at the end. Is good? So this is just all about mathing. Mathing. Okay? And guess what the next question is about? It's about finding the one variable that we haven't asked you for yet. It is about finding the concentration of A. I don't know if we have time. We've got like 3 minutes left, and we're already ahead of the other class. Maybe we should just leave this for another day. Okay? Your homework is to study for your quiz. What's your quiz on? 1.3 to 1.5. That is potential energy diagrams. What else? KE diagrams. What else? Reaction mechanisms, including catalysts. I think there's lots of like extra practice things in there if you need extra practice on potential energy diagrams and whatnot. And so, yep, that is tomorrow. And I will go home on Wednesday night. Oh, actually, it worked out really well. Thank you guys for having it. Did you guys also have a bio test today? Thank you for having a bio test today. So we couldn't do that quiz today because that means that I have marking to do during the staff meeting. It makes staff meetings feel like such less of a waste of time if I can double time. I can just listen, pay attention when it's really important. When they're just babbling or throwing pieces of paper at each other, I can just ignore them and mark, because sometimes that happens. Sometimes we do icebreaker activities. Dear God, help me. I'm sure some people enjoy them.